start recording. Wait, so this is my first time recording on Zoom. So is that all I do? All right, I'll just pretend like it's recording properly. Okay, so you guys can download processing here, and now let's hop back into processing. So this is the project that I made. Let me start a new project. So I just open up processing, open up a new project, and we can start working. So God damn it. All right, so let's start by coding some things in. Let's start off with some basics of processing. So there's void setup, which is the method that runs once when you start the program. And then there is the draw function, which keeps looping every frame. So now, so in the setup function, you would put things to set the screen up. For example, dedicate the screen size. So for example, if I want my screen to be 720 by 360 pixels, which is quite nice for what I'm going to showcase now. And you run the program, it's going to run it once, create a screen with these dimensions, and we can keep going. And I keep accidentally closing the project. I apologize for that. So let's just continue for now. Let me create a variable and name it x, and initially make it 0. So this is a float or floating point value, which is pretty much a number with a decimal. And so what I want to do now is, let me just showcase the function of noise. So what the noise function is that it gives you a random value between 0 and 1. But it turns out that this value is not so random after all, but points that are close to each other have some sort of correlation, and they are somewhat close to each other. So in the draw function, let me create a float and call it y. And what I'm going to do is that I'm going to sort of draw out what the function should look like. All right, so let's just say that the value of y is equal to the noise value. So this is a function in processing which defines the noise value for x. And then what I want to do is draw a line, a vertical line from x, y to x and the height. So what this is going to do is that it's going to just at some value at some point x or xy is going to draw a line from xy to the bottom, which is x times x and the height here. So if you run this, what you're going to see is that x is equal to 0, and we have a line at 0 here. But what we should actually do is iterate this so that x keeps increasing every frame, and it keeps and it goes along the x-axis and starts drawing these lines. So x plus plus. So what this does is that it's pretty much x equals x plus 1. So this is just going to increase the value of x every frame. And now if we run this, you're going to see that it's a straight line. It's just a black line. Now I actually know what's wrong here, and it's because the noise function gives you a random value between 0 and 1. So what you have to do here is multiply this value by the height to get so that it's proportional to the height, converting it from 0 to 1 to 0 and the height. So that, for example, if the noise value is 0.5, I want it to draw at the middle of the screen. So 0.5 times the height is going to give me the middle of the screen. And this is true for all values. So now if I run the program, you're going to see that it's giving me some very random values that seem to have no correlation. And now, this is because if we actually go into the processing reference for noise, let's scroll down a bit and let's look here. This is a key sentence. As a general rule, the smaller the difference between coordinates, the smoother the resulting noise sequence. What does that mean? That means if we keep taking smaller and smaller differences between these 2 points, it's gonna give us, well, a smoother curve, because as you can see here, this is not very smooth and this is not what we want. And the reference here actually mentions that steps of 0.005 to 0.03 work best for most applications. And what you can actually do is just try this out. So what we can do is that we can increase x by 0.05 or 0.005, but that wouldn't be very efficient, because then we're going to be taking points. I didn't mean to open that. That's for later. Is that we're going to be taking points. We're just going to keep increasing x by very small amounts, which is not what we want. What we want to do is make this the noise times a certain constant. So let's just say that this is 0.005. And now if we run this, you can see that we have a much, much, much smoother curve. So do you guys have any questions? Does this make sense? I might be going a little too fast. So if I am doing that, please tell me. Why the hell does it keep closing?
For the last line, you could just write x plus equals x, right?
X plus equals, yeah. For the last line, these are just some basic programming mathematics. So plus equals means that you're going to be changing x. So plus equals means that x is equal to x plus what's going to come next. So x plus equals 1 means that you're just going to be increasing x by 1 every frame. So if we run this again, you're going to see that it's a different drawing, but it's pretty much the same like concept. So you might realize that every time we run the program, it gives us random values of y. This is because something called a noise seed. So have you guys played Minecraft or Terraria or some other like randomly generated game?
Who didn't?
I mean, okay, so if you played Minecraft, you might realize that the word seed sounds very what's it called? Sounds very like relevant. You've heard the word seed before. So if you enter the same seed in Minecraft into more than one world, you get exactly the same world generation. Now, this is actually called a seed because if you, for example, have to exactly like if you have two tree seeds that are exactly the same, under the exact circumstances, both of these seeds are going to grow into pretty much the same tree. So in processing, or like when dealing with noise and random generation, there's something called a seed, because if you enter the same seed twice, you're going to have the exact same generation. So if we go into processing, there's something very handy. And if you go to the noise reference, so here, and you scroll down, you're going to see that there's a related section, which shows you some related, what's it called? Which shows you some related related concepts,
Functions.
I guess, or functions, yeah. Some related concepts or that are also in the reference for processing. So if we go into the noise seed, you can see here that sets the seed value for noise. By default, noise produces different results each time the program is run. Set the seed parameter to a constant to return the same pseudo-random numbers each time the software is run. So what we can do is use the noise seed function at the beginning. So noise seed, and then, for example, I want to say that the noise seed is 6, just the number 6. And if we run this once, you're going to see that it starts generating. And actually, let me increase the increments to 5 because this is going way too slowly. And you'll realize that we have a thinner color, but that's fine, I guess. And now, since we set the noise seed to 6, what do you guys think is going to happen if we run the program again? What's going to happen? Hassan, what do you think is going to happen? So we set the noise seed.
I think that there will be like a pattern for each section.
For each section.
That's what I took from you. Yeah, so I think you can just divide the first half to have a pattern. Then you can repeat it.
Okay, since you said that, I think that you might have misunderstood the concept of seeds, because what a seed is that you can think of it like a tree seed. Every time you plant the same seed under the same circumstances, it's going to give you pretty much the same tree. So yeah, it's not, well, we say that noise is random, but it's actually not so random after all. It has some sort of correlation and some patterns that you can control. And this is due to the way that it's generated, which I think is related to math, and Dana keeps leaving and joining. That's fine. All right, so let's get back to this. So Hassan, now that we have set the seed to be 6, this means that every time we run the program, it's going to give us the exact same drawing, the exact same patterns. So if we run this again, you're going to see that it's the exact same drawing.
So based on the number, it's going to give you a different pattern.
Yeah. So this is just some way that that we can control the generation of this program. Just like, as I said earlier, if you use Minecraft, for example, it's going to give you the same seed every time, or like the same world every time you use the same seed. So if we change the seed to 10, for example, it's going to give us a different drawing again. And I'm not sure if these, if the seeds that are close to each other are exactly the same. I don't actually think that.
So if you have like, for example, seed 6, then you just get a random number like seed to number 2000, for example.
If you use
Can
2000,
there be a number?
Yeah, what do you mean?
Like, is there some numbers that give the exact same seed? Or is it just that random?
I don't think that there are two values that give you the exact same seed, but that might be the case. You could try that out and like make it generate some you can make a program that detects if the seeds are exactly the same, or very close to each other at least. But I think that there is like pretty much an infinite amount of seeds that you can use. So two that are exactly the same, probably not so likely because, again, it's an infinite function. So how are you even going to know if it's exactly the same if you can't look at everything at once? All right. So now I hope that you guys have at least understood the concept of one-dimensional noise. So what if we now do something else? What if we now do something else and try to use something called two-dimensional noise? So just like we have one-dimensional noise, which varies on the on one axis or one dimension, which is x. So the value for the noise only depends on the x. What if we now make it depend on the y axis and the x axis? There's actually already a noise function set up for that. So if we stop this project and make a new project, and let's just create a float named x equal to 0.0, a float named y, which is equal to 0.0 as well. And now let's use the setup function. And what I actually want to do is only use the setup function because I've already tried this out before and trying to draw it out was not so good. All right, so let me just show you guys what I want to make. And in processing, there's something already relevant for that. So if you go into the examples tab, which you can access from file and examples, and yeah, I already had this opened because I was looking at it before just to see if it's here. So if you go into basics, into the basics examples, and this is what's great about processing is that you have references for pretty much most of the things that you might want to try out. So there are examples built into the processing program. So if you go into basics, math, and go into noise 2D, what you're going to see here is that you have these, it creates this figure that has random colors. So this is similar to TV static, but it's, I guess it's more like, how can I describe it? I guess it sort of like flows better, you could say. So let's try to replicate that. So what I'm going to do is that I'm going to draw very small cells, I guess you could call them, very small rectangles, or actually, I don't have to do that. I can just, yeah, I really don't have to do that. I can just like loop it for every single point. So what I can do is have a for loop. Now what a for loop is, I actually don't need these. I can just use variables in the for loop. So for an integer y is initially equal to 0, y must be less than the height of the screen. And then and then each iteration, I want to increase y by 1. And now, so what this is going to do is just, let me actually write the x-axis as well. That's going to make more sense. So an integer x is equal to 0. X must be less than the width of the screen, and then x plus plus. Oh, x plus plus. All right, so what this is going to do is that it's first, it's going to run the program, and then it's going to loop for all values of y, and then for each value of y, it's going to loop for every value of x. So what this is going to do is pretty much loop it for every single pixel in the program. And now I want it to draw a point at X and Y. So what this is going to do is that it's just going to draw a point. So if we run this now, it's going to be completely black. And actually, let me change the size of the screen to 720 by 720. And yeah, it takes a bit because we're looping through every single pixel. So 720 by 720, that's over 100,000 pixels that we have to loop through. But actually, your computer can handle it because it's their job to do all of this drawing, I guess. All right, so now what I want to do is have the color, or the brightness at least, of this pixel, of every single pixel, depend on the X and Y coordinates. So similar to how we had the height of this, actually let me first implement that in one dimension. So if we make it draw a line from 0 to the height at X, and I wanted to make that make the stroke, which is the color of the line, be Y times 255. So this is going to give us a value between 0 and 255. And if we run this now, you're going to see that we have randomly changing values for the color. Now, similar to how we had randomly changing height values, this is pretty much the same, but we're changing the color. And what we're going to do in the two-dimensional plane is that we're going to change the color of every single point to be related to the noise value of that point. So if we choose the noise at X and Y, or stroke, which changes the color at this point to the noise value at X and Y. And if we run this now, you're going to see that you have to give it a while. I don't know why it's completely black. I think that's because of the way that processing deals with this. Actually, you might see that it's very inefficient to deal with every single point on its own. It might be a good idea to take a set of points and draw small rectangles. So rather than changing the color of every single point, I want to create a variable and call it unit and set this equal to 10. So for every 10 pixels by 10 pixels square, it's gonna change the color of that rectangle. So rather than increase y by 1, I want to say that y is plus equals the unit itself, and x plus equals the unit. But now, now if we run this, you're going to see that, I don't know if you guys can see this, but we have these points at every 10 pixels. I'm not sure if the quality of the video shows that or not, but I can see them. And if I actually change this to, you might be able to see it if I change this to a circle with radius of 5. So now you can really, it has to be fill 0. Yeah. And now you can see these small dots, which are pretty much, so every dot pretty much represents a rectangle that we have to draw. And now at these points, I want to change the fill value, which is the color of the fill, to the noise at X and Y multiplied by 255. If we change this now, you can see that the color changes for each point. We have different colors. And if we just increase this to something like 10, or actually 15, I think, you'll see that we sort of have noise, but we don't want to draw circles. We want to draw small rectangles. So let's change that to the rectangle function, which is rect. Now for the rectangle function, which is an x coordinate, a y coordinate, and then its width and its height. So the x coordinate is going to be x, the y coordinate is going to be y, and then I'm going to make its width just the unit, and the height be just the unit. And now if we run this, you're going to see that we have all of these small cubes, but each small rectangle has an outline. So just at the beginning, I just want to say no stroke. So this is just going to remove the black outline of each rectangle. And now you can see that we have this very beautiful noise function. But you'll also realize that it's not very smooth. So so this is the same as what we did here, which is multiplying the noise value, or the value inside the noise, by some very small number. So let's try 0.005 or 0.005 and 0.005 on the y as well. And if we run this, you're going to see now that we have this very smooth, or fairly smooth value.
So is the smaller it is, the better?
The smaller it
Or
is,
just-
the smoother it's going to be. And there's something called Perlin noise, which I won't discuss now because it's not really relevant right now. And it's, so let's look at some applications of Perlin noise. Yeah, there's actually some dude on YouTube which I get a lot of inspiration from, and this project was inspired from him. So Perlin noise terrain generation. Let's just search that right now. And what you're going to see is that there are ways for you to generate height maps. So just like we generated this, if we go back to processing, we generated this color map here that we have here. What some people did was that they generated a mesh, or a three-dimensional shape, or actually some of them just used cubes, and used these Perlin noise values to create these three-dimensional meshes, or tile maps, I guess you could say. And there's another thing called marching cubes, which is similar to Perlin noise, but you can use it to generate random three-dimensional structures. So if you guys see here on the right, you can see that. And there's actually this guy on YouTube called, I forgot his name, but let me just reference him really quickly. Actually, I'll just send the video later. He does these videos called Coding Adventures, in which he uses a lot of different things. One of them was the marching cubes algorithm, which is using Perlin noise and then manipulating it in a certain way to create, I guess, three-dimensional caves, I guess you could call them. But I won't get into that. It's quite complex. It's not as simple as two-dimensional noise. All right, so now I hope you guys have like a basic understanding of how noise functions. So what I'm gonna do now is explain what I did with the other project that I've made, which is this project. So now, and I haven't sent the animation here, but you can see here that, all right, so this is called a flow field. So if you guys have studied physics, something called an electric field, or the field of electricity. And what's happening here is that in this electric field, in this flow field, every single point has a certain value, just like in the Perlin noise here. And what I'm doing here is that for each point, I'm creating a particle, and this particle, I guess, the velocity of this particle is set to be the direction of the particle actually is set to depend on the value of the Perlin or the noise value. I don't know if that was clear, but I'm sure that it will be much clearer when we get into coding it. All right, so let me again create a new project. And what I want to do now, let me open up the other one just so that we can reference it if we want to. All right, so this might get a bit into physics and using class systems. I hope that you guys are familiar with classes because they might not be so clear at the beginning. So what a class is basically just a blueprint for. I don't want to explain classes because it's going to take a long time, and then we won't have time to create the actual project. So for those of you watching this on YouTube or watching the recorded session, please go on YouTube and just search classes in programming or classes in processing, just so that you can get a basic understanding of them. All right, so what I want to do is first let me just create a screen. I just like creating a screen before starting to create any classes. So just make the size of the window 720 by 720. Change the background color to 0. And let me just run this. And you'll see now that we have a black screen. I close this again. I really should be more careful. I don't know why it keeps closing whenever I go near the edges, I guess. So if yeah, I don't know why it's closing. I'll just pretend that that doesn't happen. And what I want to do now is create a new class, or you can basically think of this as a blueprint for what a particle is going to be. So a class for particles. And I want this to have a 2D vector. So what a 2D vector is pretty much, let me open up Paint. All right, so this is what a vector is. It's pretty much a line where you have an X value and a Y value. So this is the X value and the Y value. So now what a P vector is that it pretty much just stores these two values together. So P vector for the position, and then you can reference the X position by writing position dot X. And here you can reference the X axis on this position. All right, so let's now create another P vector for the velocity of the particle itself. And I want it so that when you instantiate or create a new particle, I want it to take an X position and a Y position. And then set the position to be a new P vector with X and Y. So for those of you that are not very advanced in programming, I'd recommend just following along for now. And if you want to understand more about P vectors, excuse me, you can search about them later. But for now, I guess you could just follow along, because it's going to take a very long time if I explain everything from the basics, and I really want to finish this. All right, so what we can do now is so this is how we create a new particle. We get an X and Y position, and we put that into the position, and then we get the velocity. And at first, I want the velocity to always be 0. And yeah, I guess this is good enough for now. So in this particle, I want to have two functions, one of them called update, which just updates the position of this particle, and another function called display, which shows us where the particle is. So in the update function, I want to say that the position is so there's a function for adding vectors, so position.add, and then you put the velocity here. And what you also have to do is divide the velocity by the frame rate. All right, so let me explain some basic math. So now you've got a particle here, and the particle has some velocity. Let's just call it v. So the position of this particle after one frame is going to be, so yeah, the distance is equal to, let me use this. So the distance is equal to the velocity times delta time, or the change in time. So in this case, the distance over one frame is going to be v times, and then the difference in time, which is 1 over the frame rate. Let me just call it f for now. So the frequency, or the frame rate. So that in 1 second, if you have, for example, 60 frames, this is going to run the program 60 times. And every time you change, you take a time increment of 1 over 60. So in the end, if you add all of these time increments together, you're always going to have 1 second. So let me hop back into processing now. And so it's p-vector.div, which divides a p-vector by a certain constant. So the velocity is the p-vector, and the frame rate is the float I want to use. And now void display. Actually, let me finish this first. So what I also want to do is, as I said earlier, I want to set the velocity to be in the direction where this, so for each value in this two-dimensional noise function, I wanted to determine the direction of this particle, the direction that the velocity is facing, to depend on this value. So what I can use is noise at position.x, position.y, and use a function in processing called p-vector.fromAngle. So this is what this takes is, let me expand my screen. So this takes an angle and converts it to a p-vector that is facing in that direction. So if you use the angle 0, it's going to be horizontal to the right. If you use the angle pi, or 180 degrees, it's going to be in the opposite direction to the left. And this works for any angle. But we know that the noise function ranges from 0 to 1. So we also have to multiply this by 2 pi, or 2 times pi, so that we convert it to a full rotation. So for those of you that don't recognize this, this is trigonometry, this is math, and it's called radian. If you don't understand this and you want to understand it, search that on the internet, I guess. But what this is going to do is that it's going to create a p vector from this angle. But what I also want to do is set the magnitude. So velocity dot set mag, which sets the magnitude to be, for example, let me just say 100 for now. So this is just going to set the speed or velocity of this particle. So I can actually create a new float for that and call it speed, and I can just set the magnitude to the speed. And if we run this, oh, nothing happened. The reason for that is because we haven't created any particles. We've made the particle class, but we haven't used it. So what I want to do now, actually before that, I forgot to create the display function. So what I wanted to do is just draw a circle at the x position and y position, so position.x, position.y. And let me just give it a diameter of 1. So this is a circle function where you input an x position, a y position, and the diameter. So if you want the radius, you can have this 2 times the radius because it's the diameter. And what I want to do now is let me just define a particle. So this is how you reference classes. So you write particle and then give it a name. So let me just name it particle. And it's a new particle at 0 and 0. So this is so if you look back here, we're taking 2 parameters when we make a new particle, the x and y coordinates, and it's here. So 0 on the x, 0 on the y. Actually, let me just make this like 300 and 400 or something. It doesn't really matter. And let me go here. I forgot what I wanted to do. Yeah, and I want to make a new. Okay, so I made this new particle, and I should go and create a draw function, which repeats every frame, and make it so that this particle is updated. So we can reference the function, so particle.update. So this is going to update the particle and run this code here. And then we use the display function, so particle.display. And now it's going to display the particle as well. So now if we run this, 5, no stroke. Let me try that. Oh, you don't put anything in no stroke. So yeah, now you can see this point. And you can see it traveling along. Let me just increase its value to 2. But it's very boring when you only have one particle. In most cases, you want to create a ton of particles, which then just travel around. And this is what I actually did in this project. I just created a ton of particles and made them travel in all sorts of different directions. So what you can do is use something called an array list, or it might be easier to just use lists for now. So we can define a new list of particles like this, name it particles, and it's a new list of particles. So this is the syntax for defining a new list of particles, or an array, as it's usually called. And let's just say that I want 500 particles. And in the draw function, or in the setup function, actually, I want to loop for every single particle in this list. So for particle, let's call it P, in the list called particles. So what this does is that it loops for every single particle that we called P inside this whole list. And I want to say P is equal to a new particle at, let's give it a random value for the X and Y. So random between 0 and the width, so random width and random height. So yeah, now this is gonna make it so that every single particle is a new particle at a random position on the screen. And then in our draw function, rather than looping this initial particle, which we created, which I actually will delete now because we're not going to use it anymore, I wanted to loop for every single particle. So it's the same thing we did in the setup function. For every single particle in the list we called particles. And I want to say p.update and p.display. And if we run this now, hopefully, it's going to work. We got a null pointer exception. This means that this list has not been defined when we ran the code. I don't know what's wrong here. Because what I did was completely different in my other project. I used something called an arraylist. But I thought it would be a bit too complex to use now. So wait, actually give me a second, guys. All right, back to coding. So let's go back to debugging. This might be a bit difficult. I don't know why I got this null pointer when I clearly, Let me just try something. So I want it to only run when I'm clicking a key so that I can stop it and start it at any time. And if I run this now, give it some time. Dana asks if I can send a copy of the code. So yeah, here you go. You can copy that and copy that into your project. No problem. Great, but there's actually a major bug here, which I don't know how to fix. Let me reference my initial list.
I forgot what a null
All right,
pointer exception means.
Oh, I'm sorry, I forgot to explain that. What a null pointer is so let's talk about null. The word null pretty much means nothing or undefined.
Doesn't exist.
Yeah, doesn't exist. So when you get a null pointer exception, what the program's trying to tell you is, hey, look here, you're telling me to update something or to display something that does not exist. You never created this. But here, it should be the case that I created this new particle, but I keep getting this null pointer telling me that maybe it's in here. No, it's not in here because I defined them. Let me go back to my first code here. Let me hide the chat and that. So yeah, my code was a bit messier because it was my first time. Creating this project. So particles dot okay. Let me go back to the display function. So this is the same, but wait, it's telling me here that this local variable is not used. But it is used. That's set, I guess. Okay, back to array lists. So what an array list is because I seem to not be able to fix this small mistake that I have. So what an array list is it's like an array or a list of numbers, but you can manipulate the size of this list. So let's go back here and change this so that it's an array list. So I'm just gonna tell you the syntax of defining an array list. So it's an array list called particles, which is a new array list. And then here inside these brackets, you tell it how many initial elements or how many particles you have in this list when you first make it. So I want to make that 0. And if I run this code now, you're going to see that we no longer get this null pointer exception because we don't even have any particles. And let me remove this and let me use the mouse clicked function, which runs every time you click the mouse. And I want it to make a new particle. So particles dot add. So this adds an element to this list of particles. So add a new particle at, let's just say, random values of x and y. So random and random between 0 and the height. And if I run this now, every time I click the mouse, what? Yeah, I have to remove this. That was a silly mistake. So now every time I click the mouse, it makes a new particle. And actually, I'm getting very tired of clicking this mouse over and over and over again. So in my draw function, I want to have an if statement that detects if you're pressing any key. So key press just says, okay, if you're pressing any key on your keyboard, just run whatever's inside of here. So if any key is pressed, I wanted to add a new particle. So this is the same thing we did in the mouse clicked function. So random between 0 and the width, and random between 0 and the height. If we run this now, if I hold any key down, you can see that it just keeps making these values. And now,
can you use actually a for loop to make it?
A for loop, yeah. Smart idea. I actually did that in my code, but didn't mention that. But let's keep that for later when we want more particles. But for now, I think this is fine for now. You might want to have a for loop, like for integer w equals 0, w is less than 10, then W plus plus, and this is just going to make 10 particles every frame. So now you can see that it's much faster. So I guess we could do that if we want more particles. All right, back to coding. Now, you can see here that this particle is not very smooth. These particles don't smoothly move. Now, does anybody have any ideas for why this is happening?
Frames per second.
Frames per second?
FPS is too low.
That's actually a very good idea, but that's not the case this time. Usually, when you have a very choppy simulation, it's probably either because of the FPS or accuracy. So in this case, it's accuracy and precision. Because if we go into our function here, so velocity dot from angle, this times pi. If you remember here, we're taking the x and y values. And what's happening here is that we have these very, like, I guess, large large differences between each 2 points that the particle is going to travel across. So its velocity is not going to change very smoothly. So what we can do is multiply this by some constant like 0.00 or 0.03. Let's just make it that, 0.03. And if we run this now, you can see that it flows much more smoothly. It's like tree leaves pretty much now. It looks like tree roots or like some plant-based growth. It just resembles that for some reason. Or even hair, because hair kind of flows in this very wavy and kind of unpredictable manner. But you can also see here that we have this constant 0.03. We don't want to keep changing the code every single time we want to change this. So let's just define a new float, call it the constant, and set this to 0.03. And here, I want to change this to the constant, just so that we don't have to scroll down every time we want to slightly change the program. So if I run this now, it's pretty much exactly the same, but it's easier to change this constant now. So if I change this to 0.00005, and now I run this, it's a different value for the constant, and it's much smaller. And if you remember, the noise function is much smoother the smaller the increments you take are. You can see that here. Take as a general rule, the smaller the difference between coordinates, the smoother the resulting noise sequence. So now you can even try to take such a small difference like 0.00005, and I actually want to ask you guys, what do you think is going to happen here? It might be challenging to predict. If you change this to such a small value, the difference.
I think that'll just make it white.
Yeah. Well, make it completely white. Make everything white. That might be a good prediction, but it's actually not true. If we run this, you're going to see that since the constant between these 2 points is so close, it's so close to each other, all the particles are going to have the same velocity and travel in the same direction. So it was actually true that it's mostly going to be white, but it wasn't exactly the case. Let me now try to do something else. Let me change this constant to 0.005, like we had it earlier. I find that this is a very nice consistency between smoothness and variation. But you can see that we have a problem here where the particles keep coming so close together that they just fill the area with white. A solution to this would just be to decrease the diameter of the circle here, which is just going to make every single point thinner. And if we run this now, you're going to see some very like hair-like motion, I guess. I think that if we decrease this further to 0.5, this is going to be nicer. It might take a bit of time to get to high color, but I think it's much nicer this way. And let's talk a bit about efficiency now. So let's say that a particle goes off the screen. It's never going to, or theoretically, most likely, it's never going to come back on our screen. But in our update function, we keep detecting if it's there, and we keep updating this velocity, and we keep drawing this point, even though it's off the screen and we're never going to see it. So in your update function, you can use an if statement to say, let's just say that this is inside screen. I'll change this later, but if it's inside the screen, run this code. But you can see that this variable does not exist. So let's change this to now detect if it's on the screen. So when is it going to be off the screen? It's in the screen if its x-coordinate is larger than 0, and its x-coordinate is also less than the width of the screen. So let's write that down. So position.x is greater than 0, and then we use the expression for and, which is just this sign, and its position.x is less than the width of the screen. All right, so now we make sure that its x position is inside the screen. But what if the y position is off the screen? So we also have to write down pretty much the same expression, but for the y-axis. So greater than position.y greater than 0, and position.y is less than the height of the screen. And if we actually make this less than 500, for example, we're going to limit our screen to the point here, 500. So it keeps spawning, I guess, these particles down here, but they don't move because they're off our grid that we have defined. So let me change this to the height of the screen. So now if a point is outside, we're no longer detecting its motion, and we're no longer drawing it. Actually, let me go back here into our draw function. I don't want it to display the function here. I actually want it to display the function inside the update function, so that if the particle is off the screen, we no longer want to draw it. So, and then here, we're just going to say display. So this is just going to increase efficiency as well. So now if a particle goes off the screen, it's just gone. It's never coming back. We're never going to draw it. And you can already get this very beautiful hair-like structure. And what I find is that you are actually able to limit the angle that that this program can draw, or like the angle that the velocities can go in. So if I run this, you'll see that it's quite random now. So what if I change this so that the velocity only ranges from 0 and pi, so 0 and 180 degrees? What's going to happen now is, Hassan, what do you think is going to happen? Or Dana? Either of you can answer.
I think it won't twirl. Like it won't take a U-turn basically. This
won't
will
take a
just
unit.
be
Yeah, that's actually correct. It's
a
mostly going to
U-turn.
be, yeah, I got that. I got that. It's mostly going to be straight lines
Mm.
that are all flowing between the zero angle, which in processing is the right side. So I'm gonna go to paint. Let me paste this. All right. So here is the X and Y axis. So this is the zero angle, and the angle is going to keep increasing like this. And this is 180 degrees or pi. And now it took me some time to make some observations because of how much I messed around with this. So if I run another program, if I run this program again, you'll see that most of the particles are flowing to the left side of the screen. Why is that happening? Do you guys have any idea why this is happening? I'm guessing that you probably don't because it took me a long while to figure this out. So yeah, go ahead, Hassan.
I think that the angles, it doesn't go counterclockwise, it goes clockwise, which is weird.
Counterclockwise and clockwise. It doesn't matter like which direction you're looking at it from. So if I go into paint again, I don't know why I closed it. So since this is random generation, like yes, it's gonna make a difference in the program, but since it's random, like can we really know like the difference between if it's clockwise or counterclockwise? So this has pretty much no correlation to why this is happening. And the reason for that actually is because, okay, so let's just draw this out. And to demonstrate this, I have to use another program, which is the whole reason why I figured this out. I created another program while I was testing noise. So this is the other program I made, which just, let me make this slower. That would be nicer. So yeah, just 5. So I just made it draw lines. So this is one-dimensional Perlin noise, and I made it just draw lines randomly. This is a very bad generation. Yeah, I think that this is a bit better. So you can see here, Hassan, that most of the values that the Perlin noise generates are in some closed range. So if I go into here, and I'll just, can I draw? Yeah, I'll leave the processing window there and start drawing. So you'll see here that this is pretty much the peak that it reaches, and this is pretty much like, around here is like the minimum value that it usually goes to.
Wait, is it a sine curve?
You might
Is
think
it
it's a
like
sine curve. I think it's somewhat related to sine and cosine. I think that's how Perlin noise is generated. If you read the article posted on processing, which I did read, let me look for it. The actual noise structure is somewhat similar to that of an audio signal in respect to the functions use of frequencies, similar to the concept of harmonics in physics. So harmonics in physics, as you said, Hassan, is pretty much like sine and cosine curves. So I think it's somewhat related to sine and cosine. I haven't looked into it that much, but I think I will because it's actually quite interesting. So anyways, let's just go back here because we're going to take a long while if we start discussing that. And you can see that most of the values that we generate are in the range of around like 0.25 or like 20. I'm not using my drawing pad today, so between like around 25% and 75% of the actual value. So we never get values of 0 or 1. And if you go into processing, if you open up the sketch that we have here, you can see that the angle in which each particle flows in is never to the right. It's never at 0 or 360 degrees. It's always in some range. So if we go to Paint, I can demonstrate that here. So you can see that most of the values of the velocity are going to be in this direction. And you can observe that from this drawing. Like each particle never has a velocity to the right direction. And that is probably in most cases not what you want. So I figured out a very simple solution to this, which is to just multiply the angle by some constant, which is just gonna like fully rotate it. So rather than having the value of the angle here only depend on the noise value times 2 pi, but I just made it so that it could have an infinite or like a very large number of rotations. So for example, if we make it so that it's the noise value times 4 pi, if the noise value was 0, the angle would be 0. If the noise value was 1, the value would be 2 pi, which is going to be 2 rotations. So in this manner, what I've managed to do was increase the area that we saw here. So this is like the basic area that we covered in the first drawing, or in the initial case where we just had random values. And what this multiplying this by some constant, by multiplying the angle by some constant is going to do is somewhat increase this range. I'm not the best artist with the mouse. Anyways, so I multiplied this by around by like 4. And what that did is that it made this red circle arc here pretty much cover the whole screen, because for the value of 25, I'm not sure exactly where it's going to be, but I just multiplied the angle by some factor, which made it so that the whole circle is possibly going to be covered very often. Now, this might be the problem with random generation, is that sometimes you need to manipulate it in some ways to mold it into what you want. So if we go back into processing and we change this to 4 pi, what you're going to notice very quickly is that the usual range in which the angle faces suddenly changes to the opposite direction. But and it starts sort of negating the right side of the screen, the left side of the screen. So again, we can solve this again by multiplying this by 8, which is just gonna again increase the range that the noise value can point in as the vector. So there's actually a comment which I didn't see. My code isn't working. That was 9 minutes ago. I apologize, I didn't see that. If you want, I can copy the code here again, and you can use this. Whoa. Surprisingly, we only have 58 lines of code, which can make this very beautiful drawing. No problem. Let me leave the chat here. All right, so if we go back into processing, what we can do now, which I tried out and I really liked, was all right. So now we've got the noise value covering the whole screen. But what would happen if I just multiply this by 32? Let's just say 32. Now, what this is going to do is that it's going to increase the variation between 2 points that are close to each other. So for this point here, the vector might point here. And for the next point, it might point here, for example, or let's make it so that it's this way. So if we make a point here, it's going to go here. And then when it gets to this point, it's going to be in some other direction. Now, if I multiply this by some constant, and we have, let's just say a similar like curve. When I multiply this by the constant, the difference in these angles here is going to drastically increase. So it was some small difference. You can see here, this is some small difference. But what could happen is that this difference could be very large, like this. And what this actually results in is, anyone have any guesses? Hassan? I already sent pictures of what's going to happen. So it's pretty much just going to spiral around itself because the difference is so large that it can have full rotations before it even leaves the screen. So this is another thing you might. So if we investigate this, let me actually decrease the constant to 0.005. So this is just going to make kind of zoom in, I guess. Okay, that's too much. Is the Wi-Fi working? Can you guys hear me?
Yeah.
Oh, okay. Because my Wi-Fi was lagging for a second. All right. So I think that's a bit too small. So 0.05. I want to try and zoom in. So let me just use my very handy screen capture tool, which I don't know if you guys can even see. Let me just choose a very nice point here. Let's just say that I want to look at this. If I copy this and go into Paint and just paste that here, I can increase its size. So yeah, this is similar to what I said earlier about points that are close to each other having drastic differences in their direction. So you'll see here that if we look at this point here, or let's take another point. So this point here, it travels across here, and then when it gets to some other point, the velocity is going to change to this direction, and the next point is going to change to this direction, and so on. And this loop, this large difference in angles, is what makes it kind of spiral in this really weird way. So I hope that makes some more sense. And if you guys can successfully make a program like this, I would really encourage you guys to share it because it can really point out the beauty of math, because who the hell could have guessed that it's going to look like this without ever seeing it before? All right, so now let's try doing something else, something I haven't even tried before. I closed this by accident again. This seems to be a very big problem that I have. So what would happen if I multiply the constant here by 64? Let's just keep increasing this until so yeah, now we have some more spirals, more lines around each other, more loops. But let's see how much.
I think that if the constant is too big, it'll be like circles.
Yeah,
because
I think
they
that
just get into each other.
Yeah, it might actually, if the constant is too large, they're going to just, the points might be too close to each other, because you can see that the lines here of these circle-like patterns are getting closer and closer to each other. So maybe if we push this too much, it's like going to be too close that we're going to lose a lot of detail. So, but for now, let's just go crazy. Let's so 64 times 4, that's 256. So yeah, now you can maybe this is too much.
It's dying.
It's literally dying. My computer isn't, but this might be dying. So let me just try 108, 128. We still have these like really ugly spots, which I'm guessing loop around, which kind of like loop around itself, and it makes these like sort of like ugly spots that I personally don't like. So back to 64. Let's just stick to 64 for now. Very nice. All right, so you'll see now that if you're someone that likes colors, like me, you might want to try to color this. So give me ideas for how I can color this. Any ideas, guys?
I'm actually curious about how did you color it in the picture that you sent us.
All right, so I'll explain that now. So do you know about HSB mode? So HSB mode is
hue, brightness,
HSB, yeah, hue,
and saturation,
and brightness. So the way we deal with color in processing is that we define the, well, usually, in most cases, we use RGB mode, which is equals. Let me use equals. So this is red, green, and blue. It's telling me that my network is unstable. Is that correct, or is the program just bullshitting me?
It's actually pretty nice, so
All
I
right,
can hear clearly.
all right, because it keeps like popping up on my screen telling me your network is unstable. All right, so in RGB mode, you define values for the amount of redness, I guess you could say, in the point itself, the amount of greenness, the amount of blueness, that sounds wrong. And I've actually found, let me go back here. Let me explain HSB first. So, but for HSB mode, you're not defining values of the red, green, and blue values, but you're defining the hue, saturation, and brightness values instead. So it's easier to explain that if we go into just an online color picker that I found, which is actually very nice. Let it load a bit. And I find that this is one of the best like demonstrations of what HSB mode is, or hue, saturation, and brightness. So you can see here that the hue defines the color that we're looking at. So hue of 0 is going to be red. Hue of a lot of people use 360 degrees for the hue because it's easier to deal with when you're looking at a color wheel. But I find that to be kind of bothersome because then I would have to change all my code where I've defined the maximum brightness as 255, and I would have to change that to 360. But I'm very lazy, so the maximum value is going to be 255, and we're done. So HSB mode is where you define the hue value, and then you define the saturation, which is how strong the color is. So you can see here that the saturation changes, and the brightness is how bright the color is. So if with a saturation of 0, it's going to be completely white. With a brightness of 0, it's black. And if we increase the brightness here, you can see that the color changes. And actually, if you look here, if you look to the right here, you can see the HSL, which I'm not sure what HSL stands for, but it's some way to describe color. You can see the HSL mode, the RGB values, which are the red values, green values, and blue values, which is 0. And then hexadecimal notation, which is just another way to describe RGB mode. But I won't get into that. It's not necessary right now. So let's go back into the program, and in the setup function, I want to change the color mode to HSB. And this is actually going to have a maximum hue of 255, maximum saturation of 255, and a maximum brightness of 255, because we haven't changed these values. What you can do in processing is actually define these values. So if I want 360 for the hue, 100 for the saturation, and 100 for the brightness, I can define that in this way. But for most cases, or like in this case, I don't really want to define it. I think that it's kind of unnecessary. I can just leave it as 255 as the maximum. And if I go into my display function, what I can do is first I want to define a new float and call it the noise value. And I want this noise value in here. So rather than using this for the noise value, I want to copy that. And all right, so let me say one more thing. In processing, if you see here that I have some like irregularities in the indentation, what you can do is just click Control-T, and it's just going to fix the indentation of your whole program. So that's quite useful for cases like this where I'm lazy and I don't feel like changing it. So yeah. So first of all, the noise value is going to equal the noise value that we defined here. So this is going to be noise position.x times the constant, and position.y times the constant. And here, rather than using this, I want to use the noise value. And when we're coloring the program, when we're creating these circles, I want to change the fill value to the noise value times 255. Now, if we run this, this is not going to be colored because when you only define one point, it's gonna take it as just the brightness, and everything else is white. So you have to define the hue as this value, the brightness as 255, and the saturation is 255, and brightness is 255. And now, this is the moment of truth. If I hold down space, you're going to see that it's colored. But I actually want you guys to figure out why we're only having green and blue colors, sometimes some purple. So why do you guys think that we're getting these colors? Hassan, any guesses?
I actually don't know why.
All right, so good guess for both of you guys, but we've run into this problem before, like just now when we first made the program. And let me just yeah, this is it, I believe, right? I shouldn't have changed this, don't save, because I want to like run it again. So let me run the stream again. Wait, was it already open? Oh, it was already here. I don't know why I closed it. All right, so now you'll see here that the values of the noise are usually in this range, just like I've previously explained. So what's actually happening here is that it's the same thing that happened before, where we kind of had the particles flowing in one general direction. So if we actually look here, let me place that there. All right, so if we look back here, you'll see that we can kind of like look at this way. So you'll notice that I was wrong as to like where the values are. And actually, no, I was actually fairly correct. So it turns out that if you look at this circle here, the minimum value is like around like 25% or like around here. The maximum value is going to be, actually, no, this is correct. But because this is rotated the wrong way. All right, so let me draw a new circle. New circle. All right, so since this is the 0 angle, and most of our values in the noise are going to be in this range. So if you look at these two drawings, so if I fill this in actually, so most of the values are going to be in this red area because it's the usual range where the values are. And if you see here, you can see the direct correlation where the color is only green and blue. So a way you can fix this is actually a very nice way to draw this, to draw things out, is if you just shift this this red area. So if you add some constant to the angles, the minimum angle is going to be shifted along the axis. Excuse me, and it'll be like, okay, so how do I really explain this? So if I just add some constant to this angle, it's going to change the location of this red area. So if I just very simply go into here, and for my noise value, let me just increase this by 51 for now, and I run this, you're going to see it here that we're starting to get more pink and more purple, but we're getting less green in the drawing. And this is because, as we said again, we've shifted it, so the probability that green is going to show up is even less. And if I shift this by 102, for example, you'll see here that we're getting far more red, and we pretty much have no green right now. Like there's absolutely no green at all on the screen. And I think that, and actually here, we've got yet another problem with processing, something that is infuriating to me, which is that if you look here, the color wheel only supports values between 0 and the maximum value that you have, which is 255 in our case. So if your color value goes over this limit, processing just automatically sets it to the maximum value, which in this case is 260. I don't know why. Yeah, because 260 is the same as 0. So yeah, but in our case, it's not. Wait. So what we can do is very simply use something called a remainder. So if you guys know what a remainder is, it's like division. So if you have 5, I don't know why I ever write with my mouse. So it's, if we're looking at 5 divided by 3, this is going to equal to, this is going to be 1 plus 2 over 3, or 1.66666. But let's just write this down as 1 plus 2 over 3. So now if we again look at our full rotations, all right, so let's look at a full rotation. So we have the angle here, the angle divided by 2 pi, so 2 pi. And this is going to equal to, if the angle is greater than pi, we're going to have some number here. So let's just say that this angle is, for example, 5.4 pi. So now what we're going to have is, in this case, it's going to be 2 plus 1.4 pi over pi. So like plus 1.4. Or 1.4 over 2, actually. حسن طلع في غلط. Hello, Hassan. Your internet is amazing.
My phone just died.
Ah.
No, my phone just died.
Ah,
yeah.
Damn. All right, so pretty much all I said was that rather than using the direct value from the hue, because if we go over a full rotation, it's just going to set it to the maximum value. So what we can use is the remainder of division from this. So in this case, the remainder is going to be whatever is left over from the division that you can no longer use. So in this case, you can divide 5 by 3, and it's going to give you 1. But there's going to be another part which is going to be a decimal or a fraction. So the remainder is going to be the numerator in this case, divided by 3. And we want to take this remainder and take this value, because this is going to be the leftover from all of the rotations that we've completed. So if you have, in this case, we have 2 whole rotations plus some value that is then after the full rotation. So if we only look at this value here, which is the remainder, it's going to give us the same color value if we spin it around twice and then move it by this angle here. So if we go into processing, and actually give me a second. All right. All right, so let's get back into this. I forgot what we were doing. Yeah, let's get back to our project here. And rather than using this value, which can and sometimes will exceed 255, we want to take the remainder. So this is how you define the remainder in programming. Remainder with 255. This is what's left over from it. So now you can see that we can exceed values. We can have values over red, because what's happening now is, if you look here, what we had before was that we were missing the yellow and orange values that we have here. And the reason for that was, again, because we were exceeding the maximum value and going over it, and we had some values that are here, but they were automatically set to just be red, because the program doesn't support full rotations. Yeah, Hassan?
Okay. So what you mean is, for example, the number is, out of 255, it's maybe 270, but 270, it just is to 255.
Yeah, because
that's the math.
Yeah, because, for example,
okay.
I think the way the program works is just that, like, for brightness, for example, if you have something that's brighter than the maximum brightness, then how do you deal with this? Like, is it just the maximum? Is it just the value after a full rotation? Do you like reverse it? So the program is just set in this way. So you have to manipulate it on your own to kind of get what you want from it. So in most cases, you wouldn't even need to do this. You would just like plug it in, use the hue saturation value, and just have it colored. But in any case where you exceed maximum values, you always want to use the remainder. So let's get back into processing now. And what this actually did is that it opened up a whole range of possibilities for the ways we can color this program. So let me remove the color shift that we had earlier. And now we only have values of between green and blue. But again, just like we did earlier for changing the variety of colors here that you can see here, we can do pretty much the same thing by multiplying the value of the noise value by some constant, and that might give us values that are like 600 or maybe even more, but we're always taking the remainder, and in that case, when we're taking the remainder, it's just going to give us what's it called? The actual color value. So let me, for example, just multiply this by 8, just so that we can have a very severe difference here. And if I run this now, you'll see that we have all different colors here. So this is actually my first time trying this. So it's kind of exciting. And I think that the variety here, which is 64, let me just change this to 16 because I think that looks nicer. Because it's 8 times 2 pi. So I just thought that 8 and 8 are gonna match up pretty well. So if I run now, you'll see that you're getting some very nice coloration. And you might even want to decrease this to just 1 or something. And now it's gonna kind of flow to the left side of the screen. And you can actually see very faintly, you can see like color spots. Ooh, and I got another idea for another program I might want to make later. Yeah, Hassan, you wanted to talk?
Yeah, no, I'm just, what the hell?
This is
yeah, that looks amazing.
But I think it looks amazing. I agree, but I think that it kind of like takes away from the program. And now at this point, I'm not even like looking at the flow field. I'm only looking at the coloration. So you kind of have to decrease the coloration so that you can actually see the flow field itself. And now if I decrease the coloration, maybe in this case, I think it's still like some very severe coloration. So rather than multiplying by 2, let's just use 1.5. Maybe this is going to give us something nicer. Yeah, I think that this is a bit nicer. And we don't want too many particles that it just looks like it's just blobs in paint. So it's all about finding like the right balance of what you want. So now we can go back and keep messing with this. So if I, for example, change the constant to 0.3, just randomly, you'll see that we're getting more variety in our noise field. And very quickly in the last 5 minutes, because that's how much time we have left, because I kind of have to go. Last 5 minutes, let's just how do I say this? Let's why is my memory so bad? Yeah, I remembered. Okay, so remember what we did in our first program that we've made, which is that if we want to get the same coloration, the same drawing again, what we can use is noise seed, which I've previously explained, and I don't really have to do that anymore. So noise seed of 6 is going to give us this pattern. Let me actually use 0.005. Let me go back to my first original program and see which one looks better. It's not really a competition because I made both. So uh, yeah, I used something a bit different here, but it's pretty much the same concept. So 0.005, speed of 100, and the seed. Yeah, I made the seed a random value because I wanted to. So you can like have it as a random value. And let me just see how two programs look, because why not? I don't know why mine is going to the right. Oh yeah, it's very rookie mistake. So in our particle, this has to be the same constant. So here it was 1. Let me just change that to, let me change it to 4 as a whole. And now we're going to have 2 identical programs. So if I run this a bit, you'll see that even though it's a different program, it still makes the exact same pattern. We're using different colors, but it's still like the same overall pattern here. So yeah, I think the one I made first was better, but that might be because I'm biased towards myself. So actually, the coloration here, because I didn't like the large variety of colors, it kind of blinds you from like the concept that I want to try out. That the concept of the noise values we have here. So I just decreased this by 51, and if we run this now, it's the same drawing as mine. I think this looks better personally because we have less variety of color, which is going to make you kind of look at the actual flow field itself. Oh yeah, and let me just show one last thing off. If we decrease the constant to a really small number, it's gonna start looking like colored hair. So I don't know why it just randomly looks like someone's hair. And if you change the constant to something like 3, let's just change that to that. You're gonna have just different colors of hair, or well, quote unquote hair. And if you were to try to draw this with your hand, like by hand, good luck, because you'll probably take a very long time. Anyways, thank you guys for coming. It's been 2 hours of enjoyment for me. I've really enjoyed making this program, and I hope you guys enjoyed it as well. I really encourage you to GG. I really encourage you to try things out on your own and try to make your own adjustments to this and add your own touch. I'll send the source code on Discord if you want to access it there. I think I should make a new like channel for just source code so that send it here. All right, I'll send it here. No problem. Here you go. Ooh. Oh, look here. look here. Yeah, it doesn't support the whole thing. I don't think so. Yeah, there's not enough space. Yeah, Zoom doesn't support large text files. Anyways, yeah, I'll just stop the lecture now. I'll see you guys later. Stop share.
Bye.